Hello students, it's your online chemistry tutor, Master Delight. Today, without wasting time, we'll be looking at electronic configuration. Now, a lot of students have been asking me to do video on this very topic. Now, we said that electronic configuration is the arrangement of electrons around the nucleus of an element. That is electronic configuration. So we normally have two ways of writing electronic configuration, if not even three. Then the first one is the share electronic configuration, which is the KLMN. So talking about the share, which involves the KLMNOPQ, so on and so forth. Then the second one is the orbital electronic configuration, which involves the S, P, G, and F. Orbital. When we talk about orbital, we said that an orbital is a region where the probability of finding electron is high. A region where the probability of finding electron is high. When we talk about share, we say that share is the allowed state of electron in an atom. The allowed state of an electron in an atom. So when we talk about the KLMNO, that is the KLMNN, then we're talking about on this KLMN, then we use the formula to determine the maximum number of electrons that K can hold. The maximum number of electrons L can hold, and M and N, O, P, Q, and all of that. So we have a formula we normally use, which is 2n squared. So this 2n squared is what we use to determine the maximum number of electrons that K, L, M, N shares can hold. So now, where n equals to 1, 2, 3, 4. So for this, we have here for 1, we have K, we have L, we have M, we have what? N. So where n is 1, what is the maximum number of electrons that K can hold? Where n is 2, what is the maximum electron that N can hold? Where n is 3 for this, where n is 4 for this. So when n is 1, let's determine for K. Then we say that 2 into 1 all squared. We now have 1 squared is 1. 2 times 1 is equals to 2. So the maximum K can hold is 2. Then we look at where n is, we have 2n squared. For this is 2. So we have 2 into 2 all squared. 2 into what? 4, which is equals to what? 8. So for this, the maximum is 8. Then for n, we have where n equals 3, we have 2 into n squared. We have 2 into 3 squared equals to what? 2 into 9, which is what? 18. For this, we have 18. Then for the last one, which is 2 into 4 squared, is equal to what? 2 into 16, which is equal to what? 32. So we have for this, the maximum is what? Is 32. So for you to determine the maximum number of electrons that each KLMN shares can hold, we use the formula 2n squared. So you have this, and that. Is that clear? Now let's proceed. The formula to determine the maximum number of electrons that S, P, D, and F orbitals can hold. So the formula, we use this formula 2 bracket open 2L plus 1. Yes, this is the formula. Now, where for this, for share, the n is the principal quantum number. The n stands for the principal quantum number. Now, but for L here, for L stands for subsidiary or azimuthal azimuthal quantum number. Quantum number. So basically, we have four types of quantum number. We have the principal quantum number, we have the subsidiary or azimuthal quantum number, the magnetic quantum number, then we also have the spin quantum number. These are the four types of quantum number that we have. But here now, the first for K-share, we are using the principal quantum number, which is this n here. Then for orbital, we are using the subsidiary or azimuthal quantum number. We have to say that L stands for 0, 0, 1, 2, and 3. So you know for this, I say N is 1, 2, 3, 4, which is K, L, M, N. So, but for this, we have L is 0, 1, 2, 3. Then where this is, for 0 is S, for 1 is P, for 2 is D, then for 3 is what? Is F. I hope we are together. Now, having done this now, we now look at this formula, just the same way we use this formula to know the maximum number of electrons that each of these shares can hold. Where we have 2, 8, 18, and 32. So here, let's come to this formula. Let's look for S. Then anyway, look at the formula. The formula is 2 into 2L, so L is 0. For S, L is 0. Now, where we see L, let's put 0 in the formula. Then we have 2 into 2 times 0 plus 1. So we now have 2 bracket open. 2 times 0 is 0 plus 1. So this is 1. 2 times 1 is what? Is 2. Then S can only hold the maximum power of electron number 2. S can hold 2. Then for P, where L is 1, recall the formula. 2 into 2L plus what? Plus 1. So we have 2 bracket open. 2 times L is 1 plus 1. 2 times 1, 2 plus 1, 3. Then this 3 here times this 2, that is what? 6. So P can hold the maximum number of 6. Then we now look at, I can use this now. For D, where we have 2 into 2L plus 1, D is 2 into 2 times, D is 2 plus 1, bracket close. Then we have 2 times 2, 4 plus 1, 5 times 2, 10. So we have 10. D can hold the maximum number of 10. Then we now look at the last one, which is F, where F is 3. We have 2 into 2 times 3 plus 1. So 2 times 3 is 6 plus 1, 7. 7 times 2, 14. So F can hold the maximum number of electrons of 14. Okay. So that is it for this formula on how to determine the maximum number of electrons each share can hold. But I have this cheat for junior schools. Now, if you are writing the electronic configuration for first 20 elements, I mean first 20 elements from hydrogen to calcium, that is within first 20 elements. So you can use this 2882. 2882. This is the electronic configuration for calcium, right? 2882. So because most times students will be saying that L is 8, M is 18, but here we have 2882. This is KLMN. Students get confused. They will start saying, but sir, would it be for calcium? Why are we not making this one get to 18 before we move on to the next one? To avoid that confusion. So for students within JSS 1 to JSS 3, that's year 7 to year 9, yes. So they can use this method to write their electronic configuration. So when you are not in year 10, year 11, year 12, so you can migrate to this for proper understanding. Okay, now let's have example 1. Then the first thing you need to do when answering question like this is that you should know the atomic number of that element. So the atomic number for sodium is 11. This is the chemical symbol for sodium. So now let's write for the shell. Then this is how 1, 2, 3, 4. So we have this is our K, L, N, N. This is K, so we have the nucleus here. So now we said that N has the maximum of 32, M has 18, L has 8, K has 2. Are you with me, student, now? So now, I said if your electronic configuration is within first 20 elements, that is from hydrogen to calcium, you can simply use, I said use 2882. Now, sodium here is what? 11. Now let's draw the electronic configuration. We have 1, 2. So this is the nucleus. The first one we take 2. We are following this now. Okay, let it be my K, L, M, N. Now the first one we take 2. The second one we take 8. Then the last one, 2 plus 8, that is 10. So we have one more to make it what? 11, because we are writing for 11. The first one, the K has 2, the L has 1, 2, 3, 4, 5, 6, 7, 8. We need one more. Then one more for this. We have what? 11. So sodium, magnesium, aluminum, silicon, phosphorus, sulfur, they are all. This is for sodium now. If you want to write for 12, this is sodium. 12 is magnesium. Just add another one here. This one has become what? Magnesium. For aluminium, add another one here. This is for aluminium. Silicon is 14. So it's see, this one gets to 8 before you move to another one. Now, for example, for another example, let's write for potassium. Let's write for potassium. Now, for potassium, potassium is K, and the atomic number for potassium is what? Is 19. So it's going to be 2881. So I'm going to draw my first shell. It's going to be 2, 1, 2. I'm going to draw another shell. It's going to be 8. I'm going to draw another shell. It's going to be 8. So I'm going to draw the last one, which is going to be what? 1. Then it's going to be 2. This is my nucleus. It's going to be 2881. That is it for the first 20 elements. Now, what if you are not asking me now to write for scandium, for titanium, for vanadium, for manganese, chromium, and all of that? So we will use this one for those ones. So now let's proceed. Now let me write for sodium using the orbital. Then we have SPDF. This one is much more easier than this one. Orbital is easier than this, but they are both easy. But the one that is easiest is this. So now for SPDF 14, 10, 6, 2. So you are now asking me to write the electronic configuration for sodium. So this is how I do it. Now I will write 1s2, 2s2, 2p6, 3s2, 3s1. That is for sodium. But I have to teach you something before we start this example that will help you to understand. Now, look at this. When filling electron into the orbitals, this is the orbital, right? Now we have rules or laws that governs how you feed electron into your orbitals. These rules are, number one, we have Hund's rule. We have Hund's rule. We're looking at the rules that govern electron filling into orbitals. Rules that govern electron, rule or principle that govern filling of electron in their orbital. The first rule is Pauli exclusion principle. Pauli exclusion principle. Pauli exclusion principle states that when two electrons are filled in one orbital, the two electrons must have opposite spin. This is what that statement means. This is an orbital. Let's represent an orbital with these small balls. Now, when two electrons are filled inside here, they must have opposite spin. They must not be like this. Do you understand? If it is like this, you are wrong. So they must have opposite spin, which is one is 1/2, the other one is -1/2. Opposite direction. That is for Pauli exclusion principle. Now, looking at the second one, Hund's rule. Hund's rule states that electrons are filled singly before pairing in their orbital. Electrons are filled in their orbital singly before pairing. So that means that, for example, if I want to write the electronic configuration for carbon, let's take carbon for example now. The atomic number for carbon is what? 6. Now we have 1s2, 2s2, 2p2. This is the electronic configuration for carbon. 2p2, that was a bit terrible. 2p2. Now, having done this now, if I'm to draw their orbital, now if I fill it like this, you know this is 2px, 2py, and 2pz. Now this is my 1s, this is my 2s, and I fill this 1, 2. I fill this 1, 2. I feel this 1, 2. I feel this. How many is left? Finish, right? 2, 4, 6. This is wrong. Because according to Hund's rule states that electrons are filled singly before pairing takes place. So, for this degenerate orbital here now, we have a degenerate orbital. This is a degenerate orbital. Then I'm supposed to fill it like this: 2ps and 2p what? 2py singly before pairing. Is that clear now? Fill singly before pairing. For this 2p, what I mean here is that for this 1s, 2s, 2s, but for this p, I cannot put that 2 in one place. I must first of all fill them. Okay, let me check. Let me see for nitrogen. For nitrogen. Now for nitrogen is 7. So we have 1s2, 2s2, 2p3, right? For nitrogen, 2p3. So I have 1, 2, 3, 1, 2. This is my 1s, 2s, 2ps, 2py, 2pz. Now, according to Hund's rule, say that electrons are filled singly before pairing. I've done for this and now for this 2p now, I'm supposed to fill. If I feel like this, I'm wrong. This what I just did now is violating the laws of this Hund's rule law. Is violating Hund's law. Now, what am I supposed to do now? The law says that electrons are filled singly before pairing. So I have to fill singly, singly, singly. So I don't even have to pair because they don't have to pair. But for, this is nitrogen. For oxygen is 8. For oxygen here is going to be 4. For oxygen is going to be 1s2, 2s2, 2p4 for oxygen. So for oxygen now, I can fix, after you have done this simply, before pairing cannot take place because P will be 4. And the maximum P can take is 6. Is 6 from our calculation. Here is 2, 6, and 10, then 14. So for this 6 has a degenerate orbital, D has a degenerate orbital, and F has a degenerate orbital. So that is for oxygen, it will be like this. But for nitrogen, it will be singly. That is what Ohm's law states. Then for the last one, we have for Aufbau principle. Aufbau principle, which actually means building up of atom of electron. Now, Aufbau principle states that electrons are filled into lower orbital before the higher orbital. So Aufbau principle states that electrons are filled into their orbital in the order of increasing their energy level. Now what that means is that 1s, we have 1, we have 2, we have 3, we have 4, we have continuum. So 1s should be filled before 2s. This is the energy level. Do you understand now? 1s, 2s, 3, 4. So you fill the lower energy level before you fill the higher energy level. That is what Aufbau principle states. Now we are now looking at how to write electronic configuration using this Aufbau principle, which is what we help you in orbital electronic configuration. We have 1s, 2s, 3s, 4s, 5s. I can stop here. We have 2p, 3p, 4p, 5p, 3d, 4d, 5d, then 4f, 5f. Then you take this crossing, so now I'm picking 1s, comma, I pick 2s, comma, I pick 2p, I pick 3s, I pick 3p, I pick 4s, then I pick 3d, I pick 4p, I pick 5s, before 4d, before 5p. So it's continuous like that. So when filling electron into its orbital, you follow this order: 1s, 2s, 3p, 1s, 2s, 2p, 3s, 3p, 4s, 3d, and so on and so forth. Now let's go back to our question now. Write the electronic configuration of sodium Na, and sodium is 11, right? So you look at this place: 2, 4, this is 2, P, 6, 2 plus 6, that is 10, plus 1. So the electronic configuration is 1s2, 2s2, 2p6, 3s1. We give us sodium. Because 2 plus 2, 4 plus 6, 10 plus 1, 11. So it's very simple. If you are to write for calcium Ca, which is what? 20. This is 2, 2, 6. Here, the maximum here is going to be what? 2. Here is going to be 6. Here is going to be 2. Check. 2 plus 6, that is 10. 2, 4, 6, that is 10. So calcium, this is calcium NCl. Now, if you are not asked to write for scandium, if you are not asked to write for scandium is 21. So you just move here: 2, 4, 6, 10, 2, 4, 6, 10. D will be what? 1, right? Then the electronic configuration for scansion is going to be 1s to 2s to 2 pieces, 3s to 3 pieces, 4s to 3d1. This is for scansion. Now, okay, let me quickly do this one here. Scansion.